Hello. So we are finishing up the last section of Chapter 8. If you're in Math 90, we need to cover some matrix work because you will see this in pre-calculus when you move on. So we're going to give you a quick introduction. We're not going to go too in-depth, but it is a helpful tool when you have systems of equations that start to get large, 3 by 3, 4 by 4, 5 by 5, so on and so forth. Because as you get into higher mathematics, you'll be able to use a graphing calculator, and there's a lot of matrix options in the graphing calculator. So we're just going to go through some basics, like I said before, and introduce you to this idea of matrices, the vocabulary of matrices, and some basic operations with matrices. So this first page is going to be a lot of me reading, not a lot of work because we have some vocabulary that we sort of have to get down. All right, so 8.6, we're going to focus on solving using matrices, and then I'll briefly introduce to you section 8.7, which is Cramer's rule, but I'm not going to have you do any homework over it or test on it, just something I sort of want to show you in case it comes up later, so you will have at least seen it and be familiar with it if another instructor comes on down the line and shows you and hopes that you've seen it before. So we can say, yep, seen it before. All right, so in solving systems of equations, we perform computations with the constants. If we agree to keep all like terms in the same column, so that's a big thing with matrices, we can simplify writing a system by omitting the variables. So basically what we say is, okay, we know if you're in this spot, you're the coefficient of an x. If you're in this spot, you're a coefficient of y, so on and so forth. For example, if we do not write the variables, the operation of addition and equal signs, so if we do not write the variables or the operation of addition and the equal signs, the system 3x plus 4y equals 5 and x minus 2y equals 1 simplifies to the matrix 3, 4, 5, 1, negative 2, 1. So basically what we all agree is that we will go in alphabetical order with the variables. So this would be the x column, this would be the y column, and this would be what we call the right-hand side, or the constants. And so sometimes you see this little bar here, and that's called an augmented matrix, meaning you have the coefficients of the variable on the left and the constants on the right. The individual numbers inside the matrix are called elements or entries, depending on the textbook. Now, just like a spreadsheet, so if you've done any spreadsheet work, if you go across, those are called rows. And if you go up and down, those are columns, like the column in the Colosseum, say in Greece. So you're looking at columns moving up and down, rows moving left to right. We can use matrices to solve a system of equations. So yet another way to solve equations. So we have graphing, we have substitution, we have elimination, and now we can use matrices. Now in order to use matrices, we have to use what we call elementary row operations. So elementary row operations, and there's 3 elementary row operations. And these basically mirror what we do with typical systems when we're solving. The first row operation says that you can interchange any 2 rows. Well, of course you can, because the order that you write the equations in a system doesn't matter. So when you interchange the rows, you're just saying that equation 1 is on bottom and equation 2 is on top. So you're not changing the fundamental system. Number 2 says the elements in any row can be multiplied by a non-zero number. And that's just multiplying through by a constant. So we did this all the time with elimination, where we would multiply through by a negative 2 or by a 5 or whatever we needed to make an opposite so that we could eliminate a variable. And the number 3 is a little more complicated, but it's basically the process of elimination. It says the elements in any row can be multiplied by a non-zero number, and these products may be added to another row. So that's like adding 2 equations together, and then you get a third equation. And so that's allowed in matrix work too, only it's not as clear-cut what you're doing because you're not seeing the x, y, z's, whatever number of variables you have. The 2 matrices are row equivalent if one can be obtained by the other by a sequence of row operations. So basically what we're going to do is we're going to take sort of this messy matrix which has entries everywhere, and we're going to clean it up using row operations. So what does clean it up mean? Well, I'm glad you asked, because when we clean up a matrix, we're going to start sort of simple. And we're going to, if we start with a 2 by 2, we get to this form. If we start with a 3 by 3, we get to this form. And basically what you're seeing is a diagonal of 1 and zeros below it. Diagonal of 1, zeros below it. What ends up above that, we're not worried about, because we will be able to solve as long as we can get to this form, which is 1s along the diagonal, zeros below those 1s. And so you can imagine if you had a 4 by 4 or 5 by 5, it would be the same thing. 1s along the main diagonal, and of course that's everything on the left-hand side. Notice we're not worried about the augmented right-hand side. All right, so that's our goal. Let's get to work practicing some row operations. So the first example, and what you'll do in your homework, is just sort of practice some row operations. And so we'll go here with number 1. A says interchange row 1 with row 2. So the first thing I want you to notice is the notation. We use subscripts for the rows, and we use the back and forth arrows to say interchange, so the double-sided arrow. So basically here you have row 1, row 2, row 3. They want to interchange rows 1 and 2. And so it's as simple as it seems. If you're going to interchange row 1 and row 2, then you write row 2 first. So the top row would become 1, 6, -3, 7. And then row 2 would become 4, 12, -20, and 8. Notice row 3 didn't change at all, so it's just -3, -2, 1, -9. And that's your final answer. So that's what it looks like to interchange a row. Now, let's look at what it looks like to multiply by a constant. So if we multiply by a constant, they want us to multiply row 1 by 1/4. So multiply row 1 by 1/4. So basically we're just going to come up here and we say, all right, here's row 1, and we're going back to the original matrix, not the matrix from part A that we've changed. So, and they want us to multiply by 1/4. And so just like in an equation, you have to multiply every single term. So that new matrix is going to look like, well, 1/4 times 4 becomes 1. 1/4 times 12 becomes 3. 1/4 times -20 becomes -5. And remember, I posted that video to Facebook about using fractions in your calculator. And so that could become very helpful if you're not a fan of fractions. And then 1/4 times 8 is 2. So that's the only row that changed here. Everything else stayed the same. So I'm just going to recopy the other rows. And so we end up with the following matrix. The one should be positive, -9. Okay, now the third type of row operation. So let me switch colors again here. Go to blue. Now this one says multiply row 2 by 3, then add to row 3. And when you do this, you always get a new row, meaning we're going to replace a previous row. So what this will be is, this is the old R3. We're going to get a new row 3. And that's because your whatever row you add to, not the one you multiply by, but whatever row you add to is being replaced with a newer and improved row, meaning there's 0 or 1, something, usually zeros, that we're after. So let me show you what that looks like. So what's not changing? Well, row 1 definitely isn't changing. He's not even involved in the computation. So I'm going to go back to the original matrix. And notice the matrix has these square brackets around it, not just solid lines. And that's important to notice, because if you have just solid straight lines without the little brackets at the edge, that's a determinant versus a matrix. And you'll see determinants in a little while. So now how do you multiply 3 times row 2 and you add it to row 3? Well, you're going to come up and you're going to say, all right, I'm going to multiply this row by 3. And then you're going to add it to the row below it. So actually, before I do this, then add, and then I'll put the arrow so you're not confused. You're not multiplying that row. So I'm going to come over here to the top and multiply row 2. So 3 times R2 looks like what? Well, it looks like 3, 18, negative 9, and 7. And then they want you to add that to the old row 3. Well, what's row 3? Row 3 was negative 3, negative 2, 1, and then I'll put the line. I don't even know if you want those lines. I think that makes it look a little more messy. And then negative 9. So we're adding those up. And so what happens is you need a placeholder in there cannot be any blank spots in the matrix. So we have to put a 0, we have to put a 16, we have to put a negative 8, and we have to put a negative 2. Now this is the new row 3, and that's because whatever you're adding to, that becomes the replaced row. So our new row 3 is 0, 16, negative 8, negative 2, and row 2 stays the same. You didn't change it, you just used it as a multiplier to add to the third row. You only change one row at a time. So 1, 6, negative 3, 7. And so that's what that looks like, that row operation. So you just multiply and then add. Okay, so how do I use this to solve? Good question. The first thing you have to do is you have to translate to a matrix. So we need this to become a matrix. So the top row is going to be 1, 2, draw our line, 11. Second row is going to become 3, negative 1, 5. So that's the corresponding matrix. You just take the variables out, make sure you have an x column, a y column, and then the constants. Now, your goal is to get a matrix that has diagonals along, or ones along the diagonal, a 0 down here, any number here. We're not worried about the numbers above the diagonal, and any number on the right-hand side. So this is our goal. Right now, what do we have? We have a 1. Let me circle this. This is what we call a pivot. We always start on the diagonal. You need that to be a 1. Notice it matches this here. And it already is a 1. If it wasn't a 1, I would just divide through by a number, or I could interchange rows if there happened to be a 1 below it. So that already is a 1. Great. Now, the second thing I need to do is get zeros below that 1. So I'm going to switch colors again so I can color code this. So I need a 0 here, but what do I have? I have a 3. That's not going to work for me. So in order to solve this, I'm going to rewrite the matrix so that I can work with it a little bit better. So I have 1, 2, 11, and then what is that? 3, negative 1, and 5. So I need to get rid of, like I said, I'll do this in purple, so we kind of color coding. I need that to become a 0. We need 0. And that's just the process. It's the process of solving by matrices. Is you get a 1 in the corner, the top left diagonal 1, and then you get zeros below it. Then you go to the next diagonal, get zeros below it, so on and so forth. And so since I need a 0, I'm going to have to multiply the top row by negative 3. So I'm going to do 3 times negative 3 times row 1, because that'll give me a negative 3 in this top left hand corner, but then I'm going to add it to row 2, and that will give me the new row 2. So what's not changing is the top row as a final part. It's just going to change when I multiply and add. And remember, you only change one row at a time. So you're allowed to multiply and then add and keep the original row that you started with that you multiplied. So negative 3 times 1, kind of put it here, negative 3 times 1 is negative 3. Add it to 3 below, and you get 0. Negative 3, so we're multiplying this through, but this is just mental math. Negative 3 times 2 is negative 6, minus another 1 is negative 7. Negative 3 times 11 is negative 33, plus 5, because that 5 is positive, is negative 28. So that's what your second matrix is going to look like. So we multiplied the top row by negative 3 and added it. That's all one step. You don't consider that 2 steps. So notice when I multiply and add, whatever that final answer is, the only thing that changes. Okay, so now we have, so far, we have the 1 that we want, we have the 0 that we want. So the next thing you go to is the next diagonal entry. And so here we need a 1. Okay, no problem. So in order to get that 1, I'll just stay in the red. How are we going to get that 1? Actually, let me give me a little bit more room to write here. We are going to, you always multiply. So we're going to do negative 1/7 times row 2. And you're going, what? Fractions? Serious? Yes. Because it's really the same as dividing by -7, only the row operations are defined as multiplication, not division. So you have to multiply and add. Those are your only options. So for us, we just say, no problem, I'll just multiply by the reciprocal, which is -1/7. When you do that, -1/7 times 7, notice the top row is not changing. Bottom row, -1/7 times 0 is 0. -1/7 times -7 is +1. That's what we wanted. And -1/7, or divide by -7, the -28, and you end up with 4. So how do you read this? Well, remember, this was the x column, this was the y column. This was the right-hand side, RHS. So we hit our goal, right? We've got the diagonal that we wanted. So we've got this like we wanted. So we know if we were to put this back into equation form, this row tells us right here 0x plus 1y equals 4, or basically y equals 4. You know the value of y. Now you can go back up and plug that in to the top equation, which is not solved for x because the y entry is not 0 up here, but we're close enough. We know that, let's see if my pen comes on here, there we go, x plus 2y is equal to 11. We can always go back into variable form, but y is 4. So we know x plus 2 times 4 is 11, which is x plus 8 is 11. I don't want to run off the page here. Subtract 8 from both sides, and you end up with x equals 3. So the solution to this system is going to be 3, 4. So it's a new way to approach solving, and matrices are a little bit involved, and that's why we like to introduce them in Math 90. You'll do more work with them in pre-calculus, but I don't want the first time you struggle with this to be in a class where they're going to move really fast and expect that you've seen this before. So that's sort of our job here, is to introduce it to you, and I'll keep it to 2x2s and maybe a couple of 3x3s, but nothing more significant than that. All right, let's do another one. So number 3. So like I said before, the first thing I want you to do is convert to matrix form. So -3, 4, notice there's some space there, -1, 1, -3, 7. So again, you need a 1 in that upper diagonal right here. You need a 1. We don't have a 1. But there's a 1 right below, so guess what you can do? And you usually only do this on the very first step. You can interchange R1 and R2. After you do that, if you start reducing and getting the entries to look the way you want, and then you switch rows again, you could undo some of the work that you've done. So this is usually a step 1. If it's there, you do it. Otherwise, you don't interchange rows after that first step because you might undo some work that you've done. So if we interchange rows, it looks like 1, -3, -1, and then -3, 4, oh, sorry, 1, -3, 7 up here, and then 3, 4, -1 on the bottom. All right, so check, we've got our 1, good. Now we need a 0. You need 0. So in order to get that 0, what am I going to do? I'm going to multiply, whoops, actually I'll just write it out. We're going to multiply the first row by 3. So 3 times R1, and I'm going to add it to row 2, and I'm going to get the new R2. That means the first row is not changing. I'm just going to use him to change the bottom row. 3 times 1 is 3. Take away 3 is 0, which is what we wanted. 3 times negative 3 is negative 9, plus 4 is negative 5. 3 times 7 is 21. 21 minus 1 is 20. All right, so now you're almost there. You need to get a 1, circle it here. You need a 1 in this diagonal. So you see, the whole point of this is to see a pattern. Notice I got a 1 here in that upper left, and I went to a 0. All right, there's nothing below that, or otherwise I would go to zeros again, but there's nothing more than 1 entry below that 1. So I go to the diagonal, get a 1, so on and so forth. So in order to get rid of that negative 5, I'm going to have to multiply by the reciprocal, which is negative 1/5, and this is times row 2. Top row is going to stay the same again. Bottom row, negative 1/5 times 0 is 0. Negative 1/5 times negative 5, I'm just referring back to the last matrix, is 1. Negative 1/5 times 20 is negative 4. And so that second row gives us some information. What do we know? We know y equals negative 4. That's because this is x, this is y. And this equation says 0x plus 1y equals negative 4, which is just the same as saying y equals negative 4. We're going to substitute that into the top equation. So the top equation says x minus 3y is equal to 7, but we know y is negative 4, so x minus 3 times negative 4 is 7, or x plus 12 is 7. We'll come up here and rewrite that. Subtract 12 from both sides, and we end up with x equals, x equals negative 5. So our solution is negative 5, negative 4. It takes a little practice. It may be a little overwhelming at first, but I swear you can get this. All right, so what's better than 2 by 2? You got it, 3 by 3. So for this guy, let's go to page 2. It's a lot of the same work, it's just a little bit longer, and you may notice I gave you the whole page on this one. Yeah. So I'm teaching you to do them by hand so that you understand the process behind it, but you can imagine there's a lot of technology that comes into play when you start really working with these. So first thing we're going to do, let me switch colors here, got a new problem, is we're going to switch over to matrix form. So I have 4, negative 4, 4, negative 8, 1, negative 2, negative 2, negative 1, and 2, 1, 3, 1. All right, first thing I need is I need a 1 in that upper left-hand corner right here. I need a 1 there. I don't have a 1. So remember, what is our goal? We want to keep our eye on the prize. Well, you need to have 1s all along the diagonal, and you need to have 0s below those 1s. Otherwise, we're not worried about what is above and to the right of those 1s. So our work is all focused on the 1s and the 0s. So you have to start with the diagonal first, because if you don't, you go to try to get a 0, you can undo work. So there's a lot of strategy that goes into this. So do you see a quick way to get to that next matrix? Well, we can interchange rows 1 and 2. So let's do that. So the top row becomes 1, negative 2, negative 2, negative 1. Second row becomes 4, negative 4, 4, and negative 8. And third row becomes 2, 1, 3, 1. Okay, now where do we go next? We have to get 0s below that 1. So I need a 0 here, and I need a 0 here. So in order to get that first 0, you usually have to multiply and add to the row you want the 0 at. So I'm going to multiply the top row because it has a 1. That's the beauty of having a 1 there. I can multiply it by negative 4 and add to R2, and that will give me new R2. So what is that going to look like? Actually, let's see, how much space do I have? I think I can fit it in here. So the first row is not going to change. 1, -2, -2. Make sure I'm not going off the screen here. And the bottom row we're not working on yet. We're just working on that middle row. So -4 times the top row and then add it to the second row simultaneously. So -4 times 1 is -4, added to 4 is 0. Wake up, pen. -4 times -2 is +8, minus 4 is 4. -4 times -2 is +8, plus 4 is 12. And then -4 times -1 is 4, minus 8 is -4. So notice each step of the way you're housekeeping. So we've got 1, 0. Now I still need this guy to be 0. So how am I going to do that? I'm going to go back to row 1. I can't multiply row 2 because he's a 0 now. So I'm going to multiply row 1 again by -2. That's the opposite of this number here in the bottom left-hand corner where I want the 0. And I'm going to add that to the old row 3, and I'll get the new row 3. So the row that you're adding to is the one that changes. Nothing else changes. So first and second row going to stay the same. -1, 0, 4, 12. So those are the first two rows. Now the third row is going to change. So I'm going to go back to the previous matrix, multiply by -2. So 1 times -2 is -2, plus 2 is 0. -2 times -2 is +4. +4 plus 1 is 5. -2 times -2 is +4, plus 3 is 7. And then whoops, I didn't want to erase that. -2 times -1 is +2, plus 1 is 3. All right, and you're looking good. Look at that first column. Very nice. 1s and 0s only. So now we go to the second column, but you always start with the diagonal. So that's a 4. We need that to be a 1. So how are we going to make that a 1? There's not 1s above and below, and even if there were, I wouldn't interchange the rows because then I would mess up the work I did in the first column. So really the only way to get a 1 after that very first one is to multiply by the reciprocal. So we're going to do 1/4 times row 2. And so that means my first, I always write the rows that aren't changing. So it looks like I've done a lot more work than I really have. But the second row is changing. So 0 times 1/4 is 0. 1/4 times 4 is 1. 1/4 times 12 is 3. 1/4 times -4 is -1. All right, so I got the 1. Now I need a 0 below the 1. So that means I'm going to multiply the middle row by -5. So -5 times row 2, that's because that's where the 1 is. And then add it to the third row. And that will give me a new third row that's a little bit neater than the original messier third row, meaning there's a 0 there instead of a 5. So the first two rows again aren't changing. We're just going to have a new row 3. So the first two rows can be copied in. Move this up a little bit. So we have 1, -2, -2, -1, 0, 1, 3, -1. And then multiply row 2 by -5 and add to row 3. Well, 0 times -5 is 0, plus 0 is 0. So notice we don't undo the work we had previously. -5 times 1 is -5. Add to 5 is 0. -5 times 3 is -15. Plus 7 is -8. And then -5 times -1 is +5. Plus 3 is 8. All right, we're getting pretty close. The last thing we need is to see a 1 here. So in order to get 1s, we multiply by the reciprocal. So we're going to multiply by -1/8 times row 3. And so that looks like first and second rows not changing. 1, -2, -2, -1. 0, 1, 3, negative 1. Bottom row, multiplying by the reciprocal. Negative 1/8 times 0 is 0. Negative 1/8 times the second 0 is 0. Negative 1/8 times negative 8 is 1. And negative 1/8 times positive 8 is negative 1. And so what do we know now? What do we know? We know that this gives us, remember this is x, this is y, this is z. We know z equals negative 1. So once we know z equals negative 1, we can then go up to the row just above it. So I'm going to bring him down over here so you can see that. And basically he says y plus 3z is equal to negative 1. But we know z is equal to negative 1. So since z is equal to negative 1, we can substitute in negative 1 for z, which gives me y minus 3 equals negative 1. Add 3 to both sides, and I get y equals 2. Now I've got z and y, so I can take this guy, and I'll go to a different color, the top row. Take this one, and we know x minus 2y minus 2z is equal to negative 1. But remember, we have z equals negative 1 and y equals 2, so we can plug those in. So we have x minus 2 times 2 minus 2 times negative 1 is equal to negative 1. X minus 4 plus 2 is equal to negative 1. X minus 2 equals negative 1. Add 2 to both sides, and x equals 1. So as an ordered triple, this would look like 1, 2, negative 1. All right, so not a shorter method. I didn't promise that. I just said a different method. And matrices is really great when your systems start to get really big. So you can imagine if you have a 4x4 system or a 5x5, using elimination gets really, really tedious, even more so because you're writing out all the x, y's, and z's, and u's and v's if you have 5 variables. So this makes it a little less tedious, although still, I know, tedious. And I teach a class called Finite Math where we do lots of matrix work because you get lots of applications in business and different disciplines where you have these bigger systems, and we usually head over to the graphing calculator to start taking care of anything bigger than this. All right, so that is systems, solving systems using matrices. It's like I said, it's going to take a little bit of practice, and you may have to watch the video a couple of times. But hopefully, once it clicks, it really does click. I kind of see. I feel like I see light bulbs just flash all on the top of students' heads once they get them. So don't give up on it. Don't give up on it. And it's good brain food. It really makes you think because you got to do a lot of mental math with the multiplying and the adding. So don't give up on it. It has a lot of good qualities. Okay, the next thing I want to look at quickly is just one page worth of 8.7, and that's yet another way to solve a system called Cramer's rule. And I'm only going to show you with 2x2s because anything bigger than that just becomes really long and tedious. And like I said, I'm only doing this because if you come out of my class, I don't want you to be blindsided by anything. I want to at least have introduced you to anything that you will run against, at least in the MJC curriculum. You know, I can't guarantee what happens in other schools, but I want you to be prepared, and I want to be the one to show you, or at least give you some resources you can go back to so that you're not frustrated, because I really don't like my students to be frustrated in math. Okay, so like I said, section 8.7, we're going to look at Cramer's rule. So Cramer's rule, like I said, is yet another way to solve a system, and it is based on this idea of determinants. So let's talk about what a determinant is. First of all, notice the straight bars versus the square brackets that I was telling you about before. So when you are in my math lab, be very careful because they have a place where you can enter a matrix with square brackets and then a place where you can enter a determinant. A determinant is an operation, will actually calculate a numerical value where a matrix has entries. So very different. So matrix, square brackets, I'll write this here, determinant. you have the solid, looks like absolute value bars basically. Okay, and so a determinant is an operation, like I said, and you get a numerical answer once you know what your entries are, and you basically multiply the main diagonal, AD, and then you subtract the multiplication of the second diagonal, as I'll call it. So this is your main diagonal, and then this is your second diagonal. Okay, so how does Cramer's rule work? Well, first, you've got to calculate the determinant. So we need to know what the determinant is of this particular system. We call that determinant the main determinant D. And actually, I'll say equals D. And so I'm going to use those bars. And so the main determinant D is, take your coefficients of that left-hand side. So my coefficients are 1, 2, 3, -1. And then I'm going to multiply and subtract. So get a different color so you can kind of see it. Here's the main diagonal. So you're going to do 1 times -1, and then you're going to subtract that second diagonal, 3 times 2. And so you end up with -1 minus 6, which is -7. Now, once you've got that determinant, you still have to find 2 more determinants. So that's the main determinant. In Cramer's rule, you may notice, if I look up here, I'll just kind of say up here and up here, you're using lots of determinants. And this is the formula, and formulas are great, but I think there's an easier way to explain it. So if you want the x-coordinate of the solution, what you do is you find the determinant of x divided by the determinant of the main system. So the main system, we already found this one. This one's -7. What we don't know is what the determinant with respect to x is. Okay, good question. So all you do to find the determinant with respect to x is replace the x column with the right-hand side. So you're going to find the determinant with respect to x. Instead of the normal x column, you're going to write the right-hand side, which is 11.5, and then you keep the y column the same because you're not interested in the y right now. And so that's going to be, the main diagonal is 11 times -1 minus the second diagonal, which is 5 times 2, and that's still divided by -7. Well, 11 times -1 is -11, minus 5 times 2, which is 10, this is over -7, is -21 over -7, which gives me 3. So the x-coordinate of this solution to this system is 3. All right, now let's look at the y-coordinate. So I'll switch colors here. So the y-coordinate of the solution is going to be the determinant with respect to y over the main determinant. Well, again, that's the first thing we did, was find out what the main determinant is. So this -7 is what went here and what is going here. All right, what we don't know is what the determinant is with respect to y. So what we do is we come in, and I'm going to erase this now, and we're going to replace the y column with the right-hand side. And you can imagine if there was a z, we would replace the z column with the right-hand side, just whichever variable you're after, and you leave the other columns alone. So in this case, I'm going to leave the x column alone and just write as coefficients, but the y column becomes 11.5. And then I find the determinant. Main diagonal is 1 times 5 minus the second diagonal. That's just how you calculate the determinant. That's the formula. You may notice up here, AD minus BC. And that's still over -7. Well, 1 times 5 is 5. 3 times 11 is 33 over -7. 5 minus 33 is -28 over -7. And that gives me +4. So the solution to this system is 3, 4. And that's how you solve using Cramer's rule. It's a pretty cool method. There's a lot of algebra that's behind this to prove this, but we're just going to say that's beyond the scope of this class. And like I said, it's a neat way to solve. You learn something new with determinants, but it's not something I'm going to require you to be an expert in. I just wanted to expose you to it. So that is it for Chapter 8, and we will move on to Chapter 9 shortly. To be continued.